So example 5 continued. So I've got my delta times 1 kilonewton bar, and that's going to be equal to 5 QL to the 4 over 384 EI plus 2 times 1 over GA of the integral from 0 to L over 2 of Vx V bar x dx. So the second part of that is 2, let's just get the G8 out of the brackets. So we're looking at the area of the shear force diagram. So let's draw out the shear force diagram of half the beam. So and the value of the shear force is going to be QL over 2 at the end, and it's going to be 0 at the center of the beam. So the area of the shear force diagram, I'll just put area is equal to the half base times height. So the base is L over 2, since L over 2 is half of the beam, remembering that we're doing the integral from 0 to L over 2, so it's half times L over 2 times the height of the shear force diagram, which is QL over 2, and that's of the real system. And multiplied onto that is the value of the shear force at the centroid of the virtual system. So the centroid of the shear force diagram is going to be there, and that value up there is of course going to be constant, and that value is going to be a half. So we have our area is half times L over 2 times Q over 2, and we have the value the value of the shear force diagram of the virtual system being of course half. So let's add that together, 2 over GA, and that then becomes half times L over 2 times QL over 2, all of that multiplied by half. So cancel that out, then 2, 4, 8. So therefore we get 8 QL squared so the 8's on the underneath. So we get our 2, 4, 8. So then we get our 8 GA. So the complete solution is delta, which is the deflection, is equal to 5 QL4 over 384 EI plus QL squared divided by 8GA. And let's denote that the delta due to shear and the delta due to moment. or the delta due to bending and moment being the same. So going to Appendix 1, that tells you that this A, that the shear area of a rectangular section. So going back to the question said the section is of depth h and of width 0.5 h. So the shear area, therefore the shear area, let's just put a V there, the shear area is equal to 5/6 times the breadth, which is going to be h/2, times the depth, which is going to be equal to h, so that's 5/12 h squared. Now we're told in the question that G is equal to 0.4 E, and we know that I is 1/12 times the breadth of the section, which is h/2 multiplied by h cubed. Which is going to be h to the 4/24. So that delta, of course, is delta total. So the total deflection is going to be equal to a bending component plus a shear component. So let's just find out the ratio of delta V by delta M. And that's going to be equal to QL squared over eight times 0.4 E times 5/12 h squared, and all that's going to be divided by 5Q L to the 4 over 384 G times h to the 4/24. So simplify that down, you get 12 divided by, so that's of course E. That L becomes 2, we can get rid of the h squared and turn that one into h squared, and that simplifies to 8 times 0.4 times 5, so of course get rid of the e's, divided by 24 now, times 5L squared over 384 h squared, and then that would simplify down to 4608 h squared divided by 1920 L squared, and that's going to be equal to 2.4 h squared over L squared. And of course that equation is only valid for this rectangular cross section. Having the ratio of h for the depth and 0.5 h for the breadth. So, what does this tell you? When you use engineering theory of bending, you assume that the h over L ratio is sufficiently large. So if the length of the beam is more than 30 times, so if the length of the beam is more than 30 times the height of the beam, then this ratio of delta V by delta M is going to turn out to be 0.3%, which is tiny, which means it's normally okay to ignore shear deformation. If you have an unreasonably dimensioned beam, where the length of the beam is just twice the height of the beam, then the shear deformation is 60%, so it cannot be ignored, or it should not be ignored in calculations for stresses as well as for deflections. And if the beam is reasonably proportioned, the shear deformation works out to be 2.4%. So it's very okay in our model to ignore shear deformations. So normally engineers, the theory of bending ignores shear deformation, but you can include shear deformation if you want to, using virtual work, as we've done in the calculations here, and get an expression that allows you to include the shear deformation or the shear deflection in the total deflection calculation. So if you want it to be super accurate, you can include the shear deformation if you wanted to, following the procedure that we've done here to derive the equation.